Okay, so we'll try out an online assessment from LeetCode. So there's an online assessment, phone assessment, and on-site. Let's start with the first one. We'll have up to 2 questions. We'll have up to 1 hour. Start. Alright, this is the first question. Given an integer nums and an integer val, remove all occurrences of val in nums in place. The relative order of elements may be changed. Since it is impossible to change the length of the array in some languages, you must instead have the result be replaced in the first part of the array nums. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Return k after representing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place with O1 extra memory. Okay, so no extra space is allowed. This is the value that we have to remove. Is there an example given? Yeah, so we have an example given. So definitely we'll think about there is two options, right? We have to consider. So the idea that comes to mind is shifting, and the thing that comes to mind is swapping. Let's work with those two. So we have 3, 2, 2, 3. And what happens is, so we want to remove 3. So we want to remove this 3. So let's say, so let's say if it was something like this. I'm wondering this is even more. Let's say it's something like this. Should I sort? I mean, one of the ways could be that you sort the array, okay, and then you know where the 3 ends, and based on that you could do. But I wonder if we can do it without even sorting. So say in this case I'm at this 3. I will loop through the array till I find something which is not equal to 3, or could doing it multiple times help? Let's think of one timer. So okay, let's think of this sorting algorithm. So in case of sorting, let's say it will become 2, 2, 3, 3, and let's say what we need to remove is 2. Then we know the number of occurrences of 2. Where the first 2 starts and where the thing after the 2 ends. And no, but you're not. You can. He says you can return in any order. The relative order of the elements may be changed, right? So in that way, if I sort all I need to ensure is that those are at the end. So everything else that is before, so I'll just swap. So this 2 will get swapped with this 3, this 2 will get swapped with this 3, and we are done. How about this? How about you don't sort or anything like that, but you want to whenever you find the val, you want to move it to the end of the array. So um, yeah, sorting works. We understood that sorting will work. Now let's think of doing it without sorting. So this, let's say we want to remove 3. So we keep an index at the end. If the end itself is 3, then we'll move. And so this is a guy which next candidate for swapping, right? So we find a 3. So we'll swap 3 and this 2. So we get 3 and we get here we get 3, right? So our L will only go till this R minus 1. Okay, and then we go here too, it doesn't match. Sorry, when I swapped, it would have become 2. I think I got it. I think that's a good enough uh, approach. So I do my L to 0 and R to nums.length minus 1. Now first let's get the R to the right position. If there are already some values matching with the uh, elements matching with the value, then R should shift down. So while um, nums, so while nums of R equals to well to R minus minus. So now your R is at a good place. Now all you have to do is this int I equals to 0, or rather while your L is less than R, you check if your nums of L is matching with the val. Then what you do is you swap nums L R, and in this case your R will go one step backward further, right? Will go R minus minus, and L is always doing plus plus. And now let's what do we have to return? What is this k to return? What is the return? So return k after replacing the final result in the first case lots of nums. I don't know what is k. There are k elements after removing the duplicates. Okay, how many elements are left? Fine, fine, fine. So yeah, so I think R is a good indicator of that. Um, R is at the point. Yeah, so return R plus 1, right? Because R is at the R is at the last point of a new array. So this is fine. Now let's do swap. All right. So we see this now. Let's run and fix any compilation errors. Yeah, this is something I always mistake with the arrays and a string. Okay, so 2 2 matches, and okay, run for the other guy. I think this might be a good enough. 01403. 01403 is working. Submit. Okay, so you got an index out of bound exception. Probably empty arrays are always a problem. Some edge case that you don't understand sometimes. So if start length is 0, return 0. I think that's okay. Submit again. Even for a single element you had the same problem, but I think that shouldn't happen because what? Okay, yeah, here we are removing one, that's the thing. So okay, obviously your R will become 0. R was initially 0, now R will become minus 1, and since R becomes minus 1, So you have to do, of course, you have to do while r is greater than or equal to 0, and that's obvious. But I'm wondering when r equals minus 1, of course, but I will return r as 0, and which is correct. Which is correct. I mean, I've returned the k as 0, which is correct because after removing them, I'm left with an empty array. Okay, submit again, and I got a wrong answer. A simple problem, but making so many mistakes. Okay, 2, 2, 3. You want to remove 3, so you should have gotten 2, 2 as the output. Are your other test cases working fine now? I think so. Okay, let's run through the code. So r is greater than 0 and nums of r is not equal to val, so r remains at the last index, and then while l is less than r, nums of l equals to val, so you swap l and r goes minus minus. Because you're pretty confident that what we bring here is not the same thing as that, yes. So here my r is here, so it becomes, when I swap, 3 will come here, 2 will go there. So we are 3 to 2. Now we are at to 2. We'd always do L plus plus. And okay, now L and R both are same. Okay, that's an interesting one. If L and R both are same, then also you have to perform this because you do not know. Yeah. So if L is equals to R, then swapping also is not going to help. But you still do R minus minus. Does that help? Swap same with same, and then you go R minus minus, meaning that R now has a bad position, so you go one step back. So yeah, I think this might just work. Even okay, I think this might work. Oh come on. Oh yeah, these still work, but this ain't working out. Okay, you want to remove 4, so 0 is fine. This 4 becomes 2. This 4 becomes 0. This 0 remains as 0. Now you're at this 4, and there you are at that 4. Huh. If nums of L equals to, yeah, I think, okay, let's see what's happened to L and R in this case. So you have your 0, comma 4, comma 4, comma 0, comma 4, comma 4, comma 4, comma 0, comma 2. Okay. Uh, start with R equals to 8. Now, I think you're doing the right thing. It's just that R is on. Maybe you have to sometimes you have to return R, sometimes you have to return R plus 1, and that is where you're a bit confused, I feel. So you go. You want to remove 4, so this remains fine. This has to be 4, so you become 2. This you becomes 4. R becomes 7. We move on. This is 4, so this becomes 0. This becomes 4, and R becomes a 6. Now this is also fine. Now here we are, right? So what do we do here? Okay, so it is possible. Hmm. I mean, this could have been something else altogether, right? So I'm thinking from that sense. Basically, when you swap, the assumption that yeah, that's the thing. When you do r minus minus, you have to ensure that you always move. Yeah, so I think it's basically what you have to ensure is that you keep shifting r. This is not just here. Like I think this you have to do always. So if I put this here, to always ensure that your r is never equal to um, your r is never equal. The index value at I is not equal to L, right? I think now if I run for this, okay, submit. Oh, come on. Okay, let's say single guy. You go here, your r becomes less than r now. So you have to have that condition still, right? So you do again something like this. Um, let's take this. Okay. Finally, probably there's a better way to do it or improve with the coding style, but okay, finally it works. Let's move on to the next problem. Given an integer, okay, just one sec. All right. Given an integer of distinct integers, candidates, and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. It is guaranteed that the number of unique combinations that sum up to target is less than 150 combinations for the given input. Okay, so we have to return all unique combinations. To be able to return unique combinations, we have to exhaust the possibility of utilizing any specific number. So the candidates are distinct integers. We have to exhaust the possibility and then move on to another possibility. So it's like a DP sort of, or just a backtracking. I don't know how to apply DP as well here. If time limit exceeds, then probably have to do something, but initial idea is so let's say list of integer. List is the answer, right? So list equals to new array list, and yeah, just do combination sum. These are your candidates. You are first currently at index 0. Yes, maybe this is your target. You are at index 0. You also want to pass in like a current list or something. A current list. Yeah. Maybe, I guess. So okay, and say again. I don't think. Let me just simplify. By making it global. So we can keep it empty, and I will return list at the end. Okay, so you have your void combination sum integer array candidates in your target and your current index. If the index, well, before index, let's say if target is 0, that means the current that means you have reached what you wanted to reach. And at that point, you want to be able to return, of course, but before that, also add current. So list dot add um, new array list formed by current combination. Okay, and then you return, which is good. And if let's say you reach the index, if you reach the last and you're still not this is the target, which is why otherwise this would have happened first. That means target is non-zero. Also, if this happens early enough, which is if your target becomes less than 0, that means you added something. It's not exact, right? So which is also fine if target is 0, or basically your current sum is more than the target, or the current sum, and so adding further doesn't make sense, or current sum is still not equal to target even though you reached the end. In both those cases, just wanna just return. Yeah, nothing is possible now. Otherwise, now what you have is they have two options. One is that you choose the current guy. I think other is you don't choose. So let's say I don't choose. I go that path first. So then combination sum candidates target remains the same. I just move on. Right. That is one path. Another path is that I choose this guy. So if you choose, then your current combination, you're adding uh, this, and now your target is reduced by, and you're still at this index, and you have an option to choose it again because it's unlimited times, or you have an option to move ahead, which will just take care of in the next regression call. And you're doing backtracking always. So you remove the last guy. Think for a list it's called size. Yep. Okay, let's run. What's the issue? This is called combination sum. Yeah. So you added a extra s. Okay. So 7 and 2 to 3 works, and then let's look at the other guy as well. Okay, 3 5 2 3 3 2 2 2 2. Now the answer are probably is matching, but I think to match exactly with the answer, if you take this path first and this path second, it might just match exactly. Okay, so 2 2 3 and 7, 2 2 2 2, 2 3 3 and 3 5. Now I wonder if it will give me TLE though. It does not. That's great. Finish the session. Let's see what the report says. So the first one was easy, but we took a lot of time, and that second one probably is fine. Let's see a good solution for this one. I think I've even done it in the past. Alright, the return result shows decent. It has to be improved a bit, but not that bad. Okay, so this is my code from before. It is much cleaner. I equals 0, j equals 0, 0 is a num for length, j plus plus. If nums of, so okay, if nums of j is not equal to well, okay, I initialize some I somewhere, and then I start j, I return the I, okay. What's happening exactly? Oh, I just drag it down. Is it? I'm not even swapping. So if, okay, I mean, it's still some sort of two pointer technique. First pointer is at the beginning, second pointer is also at the beginning, second pointer goes through till the end. If the second pointer finds something which is equal to val, which is not equal to val actually, then nums of I, oh, then you put it at I. Okay, nums of I is plus plus equals to nums of j. Makes sense. Yeah, basically you just, uh, I was looking at, it's a better way to do it. I was looking at wherever vals are and trying to put them at the end. And this is looking at the guy which is not equal to val and putting it at the front. Yeah, that kind of make much sense to me. So no swapping is there at all. Yeah, much cleaner. Okay, so this is good. Maybe now let's try another assessment. So return to mock assessment. Okay, phone interview. This one has 3 questions. Let's try. Okay, we got 3 questions. First one seems like some island parameter. Second one to do with linked list. What do we have to do here? Some reordering of the list. Okay. Third one is reference of node connected and directed and something to do with the graph. Okay. Feel like I've done this before though. That's okay. Okay. Let's see the first problem. We are given a row cross column grid representing a map where grid of ij is 1 represents land. Grid of I is equal to 0 represents water. Grid cells are connected horizontally, vertically, not diagonally. The grid is completely surrounded by water and there is exactly one island. Okay. That is one or more connected sand land cells. The island doesn't have lakes, meaning that the water inside isn't connected to the water around the island. It doesn't have lakes, meaning that the water inside isn't connected to the water. Yeah, okay. One cell is a single square with side length 1. The grid is rectangular, width and height won't exceed 100. Determine the parameter of the island. Okay, I get it. So this is what it is asking for. Huh? Interesting one. Really interesting. So here is your input 0100 1110 0100 1100, and the opposition parameter is 16 yellow stripes in the image above. 1 2 3 4 5 6 7 8 10 11 12 13 14 15 16. Okay, other is just a single grid, then it's a square which is land and find, then it's 1 and 0, 1 and 0. So land and water. How is the parameter? Okay, parameter is for not making a single cell. Okay, this is weird now. I don't know how to do it. Hmm. Well, whichever cell is 1 can contribute a maximum of 4 and a minimum of okay, like this guy 0. So it can contribute from 0 to 4 edges. Okay. Start from the top left. This one is 1. So how many edges will it contribute? It depends upon, okay, let's call 4, right? Number of edges contributes is 4 and then 0 0, and now you go here. So when you go here, you can only see on its left or on its top. That's the only thing that you can already see. Nothing else is something that you have already seen. On its left and on its top, nothing is happening. So you will say 4 again. And then when you go here, on its left and on its top, uh, on both there is a, so on both that means 2. So first of all, how many ever are adjacent, right? Um, those many less you will count, perhaps, let's say. So those many less I count, that means um, I'll count only 2 then. Okay, does that make sense? Let's continue. Here there is 1, so we'll count 3. Here this guy has 1, so we'll count 3. Okay, here this guy has no, so we count 4. Here this guy has 2, so we count only 2. Let's say if it makes sense, 4 plus 4 8 plus 2 10 plus 3 13 plus 3 16 plus 4 22. No, you're getting 22. You have to reduce even further. So you only counted 2 for this because this and this is common. But if this and this is common, then you should remove from the other guys as well, not just this. So okay, let's try that again. So we start 4, then we do 4 again, and then first we subtract 2, then we do plus 2. Okay, we subtract 2 of the other of those two, and this guys we only count these two which are not adjacent to that, which makes sense to me. Okay, for the next guy there is one adjacent, so you do -1 plus 3. For the next guy, there is one adjacent, so you do -1 plus 3. Then there is no adjacent, and so no adjacent you do 4. Then there are two adjacent, you do -2 plus 2. Okay, now let's do 4 plus 4, 8. So -2 plus 2 is 0. -2 plus 2 is 0. 4 plus 4, 8. 3 minus 1 is 2. 3 minus 1 is 2. 4 is a 12. Yeah, that is actually working out. That's actually working out. Okay, then do that. So we go for die equals to 0. I must complete that length. Plus. Okay. J equals to 0. J less than length. J plus plus. Alright. Now if grid ij equals to 1 is when we are interested. I want to check two things. If I minus 1 int uh, y minus 1 is greater than or equals to 0, and then grid I minus 1j is equal to 1, then you do neighbor count plus plus, and similarly if j greater than or equal to 0, sorry, j minus 1, ij minus 1, this is equal to 0, then you do another neighbor is matching, and then you also define a parameter here. And you do parameter plus equals to so you go 4 minus neighbor count, 4 minus 2 times neighbor count basically. So if you have two adjacent neighbors, then 2 into 4 will go, so everything when you won't add anything. Okay, 4 minus 2 times neighbor count. Okay, that's the thing. You return your parameter now, and let's see if it works out. Compilation error, spelling mistake. "16, 4 and 4. Really, 16 is the one that we are. Okay, we're getting 18, which is wrong. Why is that? Thought I was doing things right. Let's quickly do again. 4, 4, 8. Then this guy has 2 adjacent, so 4 minus 4, 0. Don't add anything. This guy has 1 adjacent, so 4 minus 2, added 2. 4 plus 4 plus 2 is 10. And then this guy has 1 adjacent, so add 2 more, 12. This guy has no adjacent, so you add 4, 16. This guy has 2 adjacent, so you add nothing. It should have remained 16. So that means, yeah, it's because of this. Okay. So you get 16. Just quickly do this just to ensure you get 4 and 4. And you do submit. And you get a wrong answer right away. So for 0 and 1, you're outputting 0. Why is that? Should have added 4, no? Yeah, okay, man. Small mistakes are fine. Alright, moving on. You're given the head of a single linked list. The list can be represented as L0, L1 till Ln-1 Ln. Reorder the list to be of the following form. So you're getting L0, then you're getting the last element, then the first element, then the second last, then the second last, and so on. You may not modify the values in the list nodes, only nodes themselves may be changed. Okay, 1, 2, 3, 4 becomes 1, 4, 2, 3. A bigger example. So you got 1, 5, 1, 5, 2, 4, 3. So you got what is being done. How is it being done? Something we need to figure out. Um, it is a single linked list. So once next, let's say, is reverse of this, right? So once next is reverse of this, so you got 5. 5 next is reverse of the remaining. So if I do like that, so once next is reverse of the remaining list, which is 5, 4, 2, 3, and then you go to the 5. 5's next is reverse of the remaining list, so 1, 5, 3, 2, 4. 3 is next to the reverse, so 1, 5, 3, 4, 2, and 4 is next to the reverse, so you get 1, 5, 3, 4, 2, but it's not your right answer. Okay, so 1, 5. Let me understand again if it's making sense. So, 1, 5, 4, 3, 2. 1, 5, 2 is correct. So 1, 5, 2, 3, 4. 1, 5, 2, 4, 3. Yeah, it's making sense to me. 1, 5, 2. Here, but okay, it's like you can do it in n square easily. Is there a way to do it in overfan? That's the question. Or maybe even like if I clone the list or something like that, right? If I can save the list nodes perhaps in a stack, maybe that would be something. So if I walk through the list nodes, I'm going to keep them in a stack. So I'll have 1, then 5, then 2, sorry, no, 1, then 2, then 3, then 4, then 5. And once next to the top of the stack. So once next is 5. So basically I insert 1 between 5 and 2. Then I go to 2, which is possible to do, right? So you insert it between this once next is 5, 5 next is 2. 2 next did not change, and you now are at a 2. Now you are at 2, so what do you do then? Then what you do is 2's next is 4, so you do that as well. Okay, so 2's next is 4. That means, okay, let me think. So You start with 1 2 3 4 5. 1 points to 2 points to 3 points to 4 points to 5. You put them in a stack 1 2 3 4 5. Now you take the first guy out of the stack, put it between 1 and 2. So okay, 1 points to 5 points to 2 points to 3 points to 4 is then pointing to 5, which is pointing to, now you have a cycle. Okay, then you move to the 2 and you insert 4 between 2 and 3. So you go 1 points to 5 points to 2 points to 4 points to 3 points to 4 points to 5 is pointing to 2 and 4. But now hold on. There is no cycle. 5 is not pointed to because 5 was changed to 2.2. Yeah, but 5 is pointed to 2, right? And 4 is pointed to 5. Okay. So now you are at 3, and which is what the stack is also at, so which is when you stop, I guess. But does that mean that I change 3 is next to null? So 3 is next to null, that means 4 is next to S3. Yeah, I think that is could be, it could work. So let's try that out. So you do a stack of list node stack equals to new stack. Right now, so stack dot push, you get current dot stack dot push current equals to current dot next, right? Now while what you're saying is current is not equals to stack dot peak, till then you do, and if current is equals to stack dot push, then current dot next is null, and that is all, right? So while current is not equals to stack dot peak, what are you doing? Insert this node in between. So the insert node equals to stack dot pop, and now current dot next will be insert. Insert dot next will be current dot next. This should happen first. Right, insert, you get to a node. This guy's next is current dot next. Current dot next is insert, and then you move your current to where? Obviously not the inserted node, to the next node. So 5 gets inserted between 1 and 2. So you wanna now go to 2. So current equals to insert dot next. So this is what your thought process is here. Let's see if it works out. I think you should test it for even case. Insert dot next equals to, okay, it says insert itself, but why would you push a null guy into the stack? Why current not equal to null stack dot push current equals current dot next stack. So so that means you're now gonna push a null value into the stack, right? And you're sure that stack has a much larger number of elements, so your stack can never be null. So let's see. I think it's fine. We are pretty sure what is in the stack 1, 3, 4, 5. And I think, okay, I think what is probably missed is current is equals to head, and I think that's the missing point. Let's run again to see if it works. Huh. Stack.push. So at some point you get a what exception? Reorder list exception. Which is basically you are modifying the stack, but that should be okay, should be allowed, no? Or I can do something like this then. Simply current not equals to null. That is easier, right? If current equals to insert, you can just break here. Um, I mean, if it has a problem like that, you at some point have an empty stack. That means you never break out. I don't understand why. Let's just do it. So your current is at head. You pop element from the stack, which is 5, so just pop out 5. 5's next is equal to 2. 1's next is equals to 5. So 1's next is 5, 5's next is 2. Current equals to 5, current equals to 2 now. Okay. So basically 152. And then what you're doing is you take another element out of the stack, and this time it will be 4. So 4's next is 3, 2's next is 4, and now you are at 3. Okay. Now you remove element from the stack, it should have been 3, and so they should have matched. Current should be 3, insert should be 3, and we should have broken. So what I'm going to do now is before I pop out an element, I'll print it. So I'm also going to print out the current guy's value. And just another space to understand what's all happening. So you do. Because you're always testing on this, so okay, hold on. Maybe it works for this. Yeah, so it works for the odd case, but what you're not testing is even case. So the odd case was fine. So you go 5 1, you go 4 2, 3 and 3 are matching. But in the even case is where you have a problem. Let's look at the even case. Alright, so even case is you have 1, it is 4, you insert 1 4 2. All good. Now you are at 2 and your stack is 3. Okay, I'm missing. So think this is 1 2 3 4, stack is 1 2 3 4. You push out for 4 is what you insert, so you insert 4 between, so you go 1 4 2 3 and 3 is pointing to 4. Uh, and then what do we do? And now we are at 2. We push out element just 3. Okay, so okay, that's the thing. I think you have to stop there. So you have to stop if in two cases, if current equals to insert or current equals to insert dot not sorry uh, because you are inserting this between two guys, so you should not be any of those two guys, right? Okay, I'm inserting insert between current and current dot next, so it should not be any of those two guys. Now if I run, I just get 142 though. Okay, so for yeah, that's the problem. Okay, so here is what you have to do. Before breaking, you set this. So if current equals to insert, then and you're done with this. You don't need this now. So run code. Okay, it works here. An example test cases. 1423 and 15243 are fine. It is O of n space and time, so I think shouldn't get a problem. Yeah, more. Perhaps there's a better way, but I mean, this, if you think about it, doesn't look that bad. You have to handle an even and odd cases. That's it. Probably there's a recursion approach as well. Okay, let's do this one first. Given a reference of a node in a connected undirected graph, why am I here? Okay, let me just refresh. And read the problem again. Given a reference of a node in a connected undirected graph, return a deep copy of the graph. Each node in the graph contains a value and a list nodes of its neighbors. So the value and list of nodes of the neighbors. Okay, this return give a reference of a node in a connected undirected graph. Return the undirected is important, I guess. And connected is important, I guess, too. Return a deep copy of the graph. So you're basically creating another clone of the graph essentially. Each node in the graph contains a value int and a list node of its neighbors. So each node has a value and a list of other nodes, so the adjacency list. Okay. Now, test case format, I don't really care. For example, this is the original graph, 1 points to 2, 3. So basically here, there is an edge. It's undirected, okay? So there is an edge from 2 to 4. So one will have in its adjacency list 2 and 4. This is exactly the same. You can return the same graph. You have to create a new graph, like a new node you have to create with a different address. The nodes were cloned, but the graph is matched up with the same connections. Okay, one is not pointing to anymore. All right, so you do some sort of a DFS or something, and while doing the DFS, you also create a new nodes. Uh, you could also potentially want to save a mapping between nodes from the old graph to the nodes to the new graph to help ensure that you don't create a node multiple times. So, for example, when I'm doing a DFS from 1, I go to 2, and when I'm doing a DFS from 2, I go back to 1. Well, 1 already exists, but what is the corresponding one in the new graph, right? So I need to maintain a map of nodes, that's for sure. So that's one thing that I might need, which is a map node uh, map. So I might definitely need a new a mapping between one-to-one mapping between the nodes of the graphs. Okay, let's just do DFS. What do you say? So okay, so you do DFS with just node. Do I need a visited array or something like that when I'm doing DFS? So let's just think. So when I'm starting from 1, what I'll see is that, hey, first create a node for 1, obviously. Then go to its children. So first I go to 2. I create a node for 2. Or wait, hold on. So when I'm starting at 1, for all its children, I can create corresponding nodes as well, right? And the corresponding edges. So whatever information I have from 1, I could populate all of that. Which is I from 1, I know there is adjacency list contains 2 and 4, so I can just replicate this entire part 1 2 4 part. I can replicate just based on 1, right? And then when I go to 2, obviously corresponding to 2 there is a node. And then 2, would I have created 2 to 1 already? Let's say assume I would have, right? When I created, so I already did 2 to 1, so I don't add a node from 2 to 1 again. uh, so you ignore all of those nodes which are already existing, only the new nodes. So you see 3 here. 3 is a new guy, so you add 3. I think that's all, right? So okay, I don't know if to how much you understood, but I think it's you need a visited in short here. So you need a is visited the right word? Let me think again. So uh, it's a connected, right? It's a connected graph. Everybody is connected to everybody, but it's undirected. So you can't. It's not a directed graph as well. So it's not like, hey, I'm finding an edge from 3 to 1. If there was an edge from 3 to 1, I would have found it from 1 itself. So if somebody has been visited, I do not have to worry about it at all. So let's say there was a. So I mean, so for example, from 3, if I've already done with 2 and 4, I'm at 3. I don't have to worry about uh, an edge from 3 to 1, an edge from 3 to 4. I don't at all. Let me think this way. So when I start with 1, what all do I do before I come? Will I have added 4? See, it's whether I'm doing a BFS or a DFS. If I'm doing a DFS, I would have from 1, I would have gone to 2, and then I would have added everything between 1 and 2. And from 2, I would have gone to 3, and I would have added like an edge between 2 and 3, created edges completely new nodes as well. From 3, I would have gone to 4. I would have added an edge between 4 and 1. From 4, now is the point. Now from 4, there's an edge to 1. 1 is marked visited. So do I add an edge? I think if it's marked visited, you don't do anything. Okay, and then when I'm looking at another path from 1, which is 4, that will take care of it. But is 4 visited? Yeah, now I see a problem, right? Okay, so let's do this. Let's do a DFS traversal. Okay, so DFS traversal is you start from 1, you go to 2, from 2 you go to 3, from 3 you go to 4, from 4 you see a 1 which you don't do anything about, then from 3 you see any other edge, not that is not visited, any through any other edge, not that one that is not from 1 any, no. Okay, so will you miss out on adding an edge between 1 and 4 if you just do a regular DFS? When you start from 1, you add an edge between 1 and 2. 2 to 3, you add an edge between 2 and 3. 3 to 4, you add an edge between 3 and 4. From 4, do you mark the 4 as visited? Because you are calling on DFS on this, so you mark it visited, yes, and now you're visiting its edges. So from there is an edge from 4 to 1. 1 is marked visited. Hmm. 1 is marked visited, so you want to ensure that, but you want to add an edge, right? Hmm. So how do you slightly modify the algorithm to ensure that you add an edge between 4 and 1? And for that matter, like if there was an edge between 3 and 1, you want to ensure that you add that edge. Feel like a BFS might be much simpler here. What do you say? So one, no, so you have to think it in like that sense. You are traversing all the edges. Yes, you might have visited somebody, but the edge is new, right? That's why you're visiting it now. Otherwise, you would never have. But you can't always say the edge is new because, like from 2 to 3 when you came, 3 to 2 there is always an edge that is being repeated. So, so this is my take here, right? So from 1, when you're adding uh, edges, you only add the edge in one direction. Don't add the edge in another direction. I think that's let the edge in another direction be added when you are doing the DFS from 2. That way, what will happen is, so from 1 when you start, you would add a node 1, you would add a node 2. In the adjacency list of 1, you will add 2. Then you would add 2. When you are at 2, you see there is an edge from 2 to 1. 1 already exists, so you just add the edge. That's all you add, right? Just the edge uh, in the cloned graph. And then if you see 2 to 3, 3 does not exist, so you add the 3 node, you add a 2 to 3 node. Now you're at 3. There's a 3 to 2 edge, then 2 node already exists, so you just add the edge. There's a 3 to 4 edge, 4 does not exist, so you add the node, you add the edge. Now you are at 4. Now you're at 4, so you add an edge from 1 to 4. So from 4 to 1. Now you're back at 3. Is there any more edges? No. Now you're back at 2. Are there any more edges? No. You're back at 1. Any more edges? Yeah, there is from 1 to 4. 4 already exists, so you just add an edge. I think that makes perfect sense to me. Let's just code that out. So I'm doing DFS node. So I need to visit it. I probably don't need visited because visited. It already. It exists in this node. That means it is sort of visited. Okay, that makes sense to me. So just a snap. So then DFS node. Uh, let's see. Void DFS. But you want to return something, no? Yeah. So you return this. You return map.cat of this node. Fair enough. Node now if so first thing is you're at a node, does that node even exists, right? So if not, map dot contains key node, then you do map dot push, not push, put. Corresponding to this node, I'm adding a new node with the same value as node.val. Okay, so now you get the cloned node. And what are you doing here with this cloned node? What am I doing here? So corresponding, yeah, I think it's changed a little bit, but okay. So I'm doing a DFS starting from 1. So first I add a node for 1. I mean, I think I expect this to always be present, but that's probably okay. So now for each node in the adjacency list, also for each node, you can call neighbor in node dot neighbors. I can just say do DFS neighbor. Does that make sense? That would only create the nodes if they don't exist, right? Where would you add the adjacency lists? So you do this. If the neighbor doesn't exist, then you node equals to new node. Uh, no, I can't neighbor node. Just call it new neighbor node. Equals to. I just call it neighbor node or clone neighbor, right? If map does not contain it, then you add new node with neighbor.val. Now you go else. You don't have to do an else, right? You can again just do I think you should do map dot put here. This makes sense. And then you do and you remove this. If the node doesn't neighbor node doesn't exist, you add it, and you get the clone neighbor node. And what you want to do is this: map.cat of node dot in this guy's adjacency list. Is it a list or is it an integer? It's a list, which is good. Called neighbors. Yeah. In this, you add the clone neighbor node. All right, and you call user neighbor, which is okay. Yeah, I think this is fine. Now let me wrap my hand around it a little bit. So only for the first node is where this would be the case. So maybe I just create one. Yeah, I think that's fair. So map.put node new node node.val. Then we're pretty sure that whichever node is I am traversing already has been created. Okay, let's understand it again. So for one, I have created a duplicate node, and that duplicate node is this map.get node in its neighbors. For all the neighbors, so 1 to 2, 2 to 4, or I will end up adding those if they already exist. If they don't exist, I'll create. If they don't, or if they already exist, then I'll just get them, right? And I'll add in the adjacent list of one of those neighbors. Now fine. When I'm at 2, there will be an edge from 2 to 1, right? So in 2, I will add in my adjacent list. I will add one. That's for sure. But one already exists. I won't add it again. Yeah, I think it works. Let's just do this. Um, Stack overflow. Node clone label equals to map.get neighbor. Can your node be null? According to DFS on neighbor, neighbor cannot be null. Okay. When you do a DFS on your neighbor, but if the neighbor is something that already exists, then you don't want to go into that loop, correct? So either you don't call it, and which is, but now it already exists, right? So perhaps then you do this. If the neighbor already exists, hmm, I mean that's a weird place to be in. I mean, two now exists, right? I mean, I get you could have a visited as a separate guy and deal with that, which I can totally agree with. So one is now visited, right? So two, when you create, it's not yet visited though. So you don't want to go at two and you want to do these things, all right? You could sort of rely upon those visited bit by the fact that if this wasn't the iteration that created it, I think just have a visited one. It's okay. Okay, should be fine. Null pointer exception. How can your node be null? I don't understand that. Just the visitor is null. Okay, because you did not initialize visited. Fine. Okay, let's see. 2413, 2413. Yeah, I think submit and see if it works. I think I did not. I probably won't. Yeah, fine. For an empty, yeah, all those things I did not handle. What if the graph is null? Note that the input contains an empty list. The graph consists of only a single node with value equals to 1. It does not have any neighbors. Let's do this. Come on. Let's run for all examples. I basically want to see whether it works for the second one. And it will fail for the third one. Okay, can't tell, huh? Sample test cases. Remove this, and this. Go with that. Okay, this one works. So the only case that does not work is here node by itself will be a problem. So if node equals to null, return null. Okay, let's just submit. All right, done. Easy, medium, and medium. Island parameter, I think. How did we do? So this is what we did in the island parameter. Yeah, basically we figured out if there is an adjacent nodes. When you find an adjacent node, what to do with that. Fair enough. Not that good of a score, but okay. Reorder list, we did a tricky way. Okay, as you can see it here. We use extra memory, but we did it in O of n. And yeah, we took care of even and odd cases separately, but other than that, it was all sort of straightforwardish. I don't think there is a way, either you do it in n square or you do in O of n, right? If you don't want to take up extra space, then you could probably do it in O of n square, but yeah, this is fine. Clone graph. Don't need to open here. Just open here. Yeah, we did the DFS. The code doesn't look that big. This is a case that we first handled mishandling, which is fine. We handled, and then basically we're doing a DFS. And while doing a DFS, you're not adding both the adjacency lists. Like when we are doing 1 to 2, only then we add an adjacency list of 1 to 2. And then when we are at 2, we just added 1 to 2 adjacency list, and that way everything happens fine. We use it to ensure we don't go in cycles and so forth. All right, I think this is good enough for today. I'll stop here.